Good morning, everybody. Again, for those who were here, it's already we talked. Anyway, the thing with it is there are two items in here that I really want you guys to be aware of, extremely important for those who are live and for those who are actually watching this recording later. The first one is the review exam. It's on Canvas. It's available for you guys, and you should have done it. If not, please do it as soon as possible. It should help you prepare the exam. And also it's for credit too, so it's not like you want to skip it really, because if you skip it, you're going to be missing on points. It's a participation quiz. The rule for it is similar to the first review that we did before exam one, meaning that it doesn't matter how much you score in it. Even if you get one correct answer out of 178, it doesn't matter even if you get them all wrong, or if you get them all correct. So in this case, you end up with full credit because you have taken the time to go and do the review. So in other words, you're working on your classroom, so you get full credit for it. Again, you're going to go through all of the questions. So you really should come with probably a state of mind that you're going through a preparation. So you take notes, make sure that you know what the question is, make sure the answer, you're comfortable with it, and things like that. It's a lot. That's why it has no time limit. So you're going to go through it, take your time. I would suspect a minimum of a couple of hours is required for this one. I mean, I would want you to take as much time as possible on this one. Of course, minimum spend about a couple of hours. So if you don't have that time today or tomorrow, try to dedicate at least that time during the weekend so that you spend the preparation, you give it its full rights, its due rights, so that you're ready for the exam. The review will close on Monday at noon. Usually things with me, and you have probably noticed that, I make things expire by 11 p.m. at night. Everything almost, all of the assignments, with the exception for the exams. And this review is an exception because the exam will open at 10 p.m., which brings me to the second point that I wanted to bring attention to everybody in here. The exam is at 11 p.m. I mean, it starts at 10 p.m. on Monday and goes all the way to 10 a.m. Once you start it, though, you cannot pause. You have to finish it. So if you are a person who basically can stay awake during the nighttime and full aware and focused, that's probably it's okay to start it at 10 p.m., meaning that you're going to get about an hour and a half sitting on the computer, working on your exam, and you're done with it, and you submit it, and you're fine. You start it full focused, and then 20 minutes down the road, and you start sleepy and tired, and you lose focus. That's not good. Okay, that is if you're a person who is an early riser like myself. Okay, the person who wakes up in the morning can still get their coffee, can still basically do their breakfast, and go back no later than 8:30 in the morning to start the exam, because the exam will end at 10 a.m. So that is basically the caution that I am coming with in here for everybody. So don't start it unless you are basically focused, you know what you're doing. Hopefully you get 100% out of it, okay? If not,
Professor.
I'm sorry?
I have a question.
Uh-huh.
I saw that the week 7 quiz has 40 questions on it, and I was wondering if it's okay if we lower it to 20, because I think, again, like that's more of an exam than a quiz.
No, actually the points are not the number of questions.
Okay.
Yeah, I think the points are not the number of questions. I think it's the quiz 2. No, they are not the number of questions. Hold on, let me check. Which one you're talking about?
The week 7 quiz?
Week 7, it's 40 points. Let me check to make sure, okay? Yeah, like I said, the number of questions actually is 20. It's half that much.
Okay, thank you.
Yeah, the number of points is is more than, it's twice basically, because some of these questions actually, and Sarah probably have noted them, is that gives you, okay, option A, which is correct, and option B, which is correct, and then there are only, you have to, and then option C, which is sometimes says both of them, or tells you which one is not correct, and there are three of them that are correct. So I'm allotting in here for partial credit for some of these questions. That's why I will go back and regrade them. So instead of getting the entire question wrong because you choose part A, which is correct, you're going to get partial credit. So that's why I changed a little bit the grading schema so that I can go through them and see that people sometimes are correct in a sense, at least partially correct, so they get partial credit for it. So that's something that is, so the exam, you have to really, like I said, also has, I think the grades also are not necessarily the number of questions, is also, like I said, is very important that when you start it, you finish it, okay? So please, please, please make sure that you're fully focused. Do not start it at 2 a.m., half asleep, and then you wake up and the exam has closed already on you. So that's basically my warning, okay? That's the only thing I wanted to say in terms of the exam, both the review and the actual exam, okay? Other than that, I'm going to try to make although the topic today is very important, so I'll try to make it a little bit as fast as we can so that you guys can go back to the business of exam 2. But don't forget, exam 3 is not too far away, so that's why this topic is not, we should not really also neglect it, okay? So, you guys don't have any questions, we can go to chapter 13, which is the atomic nucleus, or the nucleus of the atom, and the concept of radioactivity, which is a process that happens on the nucleus itself, inside the nucleus of the atom. So we talked about the structure of the atom, and basically we saw that it has an electronic cloud and a nucleus. Today we're going to focus mainly on the nucleus itself and what's going on in it. And basically, the biggest thing that basically amazed people for a long time, phosphorus was one of them that glows at night, and other things was this radioactivity, okay, the concept of radioactivity. And that is sometimes elements by themselves, spontaneously, they glow, okay? You don't need to do anything on them, and they emit radiation, okay? So we are submerged in this effect. And the sources for that on a daily experience are two. Okay, one of them is coming from the outside of the Earth, and that is basically cosmic radiation. And the other one is actually from the Earth itself, because it has materials that are radioactive by themselves, and they produce radioactivity. And for the most part, that is actually the source of heat inside the Earth. Okay. So that's basically some of the things that can be produced by that. We're going to talk about the forces causing that, because it's not any force that we have discovered yet. It's not the force of gravity. It's not the force of electricity and magnetism, namely the electrostatic force, the fact that two positive charges repel one another, two negative charges repel one another, a positive charge and a negative charge will attract one another, and we can follow Mr. Coulomb's law to find exactly the strength of that force and the direction of that force. No, actually it's another kind of force altogether, and they're the so-called strong nuclear forces. That is what they bind the atom altogether. Now, the radioactivity is not really strong nuclear forces either, okay? So it's none of the above, technically. It's not gravity, it's not electrostatic force, it's not nuclear strong forces, it's the so-called nuclear weak forces, and those are the four forces of nature. This is topics today, okay? The four forces of nature, that's the discussion, are the force of gravity, the electrostatic force, namely the electrical force, okay? Electricity and magnetism, they reside on that. On a day-to-day experience, this is really what we deal with, the electrostatic force. If you shake hands with somebody, it's your electrons and their electrons interacting with one another. You see something, it's the electrons basically in your eye that are responding to the excitation and the the electric field and the magnetic field produced by light. You hear something, it's because the pressure, because of the motion basically inside the in the air, that basically exerts on your ear, and that pressure is transmitted as a signal, namely electrical signal, all the way to your brain, which gives you a sensation of what this sounds like. You smell something, again, you're detecting those ones inside your nose. So the taste, everything that we do day in, day out, the reason why I cannot go through walls is because of the electrostatic force. The reason why I'm sitting comfortable again in here on this chair is because of the electrostatic force. So this is a daily thing. We deal with it on a daily basis. The gravity also plays a major role in our daily lives. It's what glues the entire universe together. And as a matter of fact, what keeps us on the Earth. Otherwise, we will not be able to sit on Earth. So those two forces are the main forces on a daily experience. However, without strong nuclear forces, we would not be here either, because the entire nucleus will be unstable, and we will see that. So the reason why we have atoms to begin with is because of the nuclear forces. So they play an indirect role, an unforeseen role behind the scenes that keep everything from falling apart, and they are the nuclear forces. Okay. If it were only to electrostatic force, no atom can exist the way it is, except hydrogen atom. So that's the nuclear forces for you. And then these weak forces that are responsible for the so-called radioactivity. So those are the forces, four forces in nature. In terms of strength, how strong they are, I'm going to rank them from the least to the highest. Let's say, for example, between you and I, this is how strong gravity is. It is very, 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 very weak force. Okay? If you are going to put a number on it, it's divided by 1 followed by 40 zeros, or if you wish, 0.39 zeros and a 1 at the end. So it's super weak compared to what? Compared to electrostatic. So this is gravity. This is electricity and magnetism, electrostatic force. Static. Okay? About 100 times bigger than this, stronger than this, not that much, but 100 is enough, is this one, the strong nuclear forces. Okay? Weaker than that, actually, somewhere in here too, is the weak weak nuclear forces. So nuclear forces are called strong for a reason. Okay? Strong nuclear forces. They are actually super strong, and they have to be in order to do what they need to do. Okay? We're going to talk about basic properties of basically radioactivity. Namely, the first one is half-life. How long does it take for a substance to lose half of it what we started with? So if I started with 1 kilogram of a substance, and I know that it's going to change to a different substance, I will wait for so much time when half of a kilogram now is a new substance, and the other half, of course, the other substance. So that's the half-life. And then transmutation is this operation itself, going from one element to completely different element. Okay, this was the dream of alchemists in the old days. They wanted to basically make gold out of iron. It turns out that they were right, but it's not chemistry that do that for you. It's nuclear reactions that does that for you. So you can't make gold out of whatever you want to. The thing with it is, it costs more to make gold than the actual gold you end up with. That's why it's not really an efficient operation. So the dream came true, except that it's a costly price, so it was abandoned at the end. Okay. One of its applications is radiometric dating, namely carbon dating is one of them. For example, for living materials, you can date, for example, a specific log or whatever that is that you can find. Obviously, the accuracy of that, because it's in the thousands of years, is not precisely. You cannot say this was made in such and such year and such year, but you can come up with a margin of error for that. Of course, it's used not just for carbon, but it's used also for other things. And this is one of the really branches of astronomy that astronomers are always looking for those meteorites that come from specific regions because they will tell you the history of the solar system altogether. Okay, if you know how much substance I have, how much uranium, for example, 238 of how much, for example, potassium do I have in there. So if I know those, then I can date this, and I know the structure of the early solar system. So it's really a good tool to do historical, basically, analysis of what's going on, and probably also make predictions for the future too, based on these things. So it's an important aspect of geology, and astronomy, and other things that is used for this one. So radioactivity plays a major role in terms of that. As a matter of fact, there is another thing I didn't mention, and I know we're going to mention it down the road when we do astronomy, but it's worth mentioning. Without it, there could not be heat enough inside the Earth to create a magnetic field to protect life as we know it, because this radiation that we're talking about is coming from the outside also of the Earth, especially from the sun and the rest of the galaxy, and that bombards the entire Earth on a regular basis. And it's that magnetic field produced by the core of the Earth that protects the Earth itself and life on Earth. Okay. We're going to talk about nuclear fusion and fission, actually part of the process. And we will understand then that basically there are two sides of the mass to energy curve. And for the protons, for the nucleons, that is. And on one side, we have fission. That is on this, on the side heavier than iron. On the other side, less than iron, we have fusion. And these processes can be energy efficient if they are done correctly. And we will understand then that iron is a cutoff. Iron is really a sink when it comes to this energy. And iron plays a major role when it comes to stellar evolutions, how stars evolve, because stars make elements all the time. That's how basically we got all of the elements in the universe, other than hydrogen, basically, and some helium. Except once they reach iron, at that point the star would have signed its own death, basically, certificate. It's dying. It will die immediately. Okay, some stars are not big enough to do that, like for example the sun. It's not going to reach that stage, but others they would because of their sheer size. And once they do that, they will go supernova, and that's their end, basically. That's how they end. So you will understand that connection today. So this is in a nutshell today's topic. We're going to talk about nuclear fusion also. And part of the problem with nuclear fusion is that you take light elements and basically bring them to high enough temperatures to get rid of their electrons. And the problem with that is now they will be, the ions, they will be positively charged and repel one another. What you want to do is you want to bring them close enough from one another. Once they're close enough from one another, this electrostatic force will be negligible in front of this big strong force. So they will fuse, actually. Okay. So you have to spend a lot of energy bringing them together. Once they're close enough, they will fuse and give you more energy than when you started with. So this is an effective process. This process is actually, it will give you more energy than when you start with it. So this is an exothermic nuclear reaction, which means it's going to give you more energy, and the energy that you will end up with is more than what you start with. The trouble with is to keeping this ionized, which is a plasma state, really, close enough, okay, without exploding and getting into a nuclear bomb, really. So that's part of the challenge that physicists and applied physicists and engineers are trying everywhere, trying to make abundant energy using nuclear fusion, not nuclear fission, not nuclear reactors. Most of the nuclear reactors nowadays, they use this process, which is easy. I mean, compared to the nuclear fusion, it's a lot easier, okay, to do. If you're wondering what's going on inside the stars, this is what's happening inside the stars. It's nuclear fusion. So that's what fuels the stars. It's this operation. So, radioactivity. So today's topic is about the four forces of nature and where we stand. We started with gravity and electrostatic force. We call it friction, we call it normal force, we call it all kinds of other names, but it's actually still electrostatic force, okay? And we will see it probably in more detail down the road, but this is basically the two forces. Then today we're discovering the other two. So those are basically the four forces of nature, and you have to know them. Every other force, a push is actually an electrostatic force. A pull is actually an electrostatic force. Everything else can be one or a combination of the others. That's basically how this boils down to. So there are four forces in nature. There were some papers, I think last year, that people claimed the fifth force in nature that explain why some parts of the universe are probably repelling from one another, but it's still not confirmed. So this is what we know today. In nature, there are only four forces, okay? So radioactivity results from a radioactive decay, which is a process whereby unstable atomic nuclei transform and emit radiation. And it has existed from a long time ago. So this is not a process that is due to politicians or due to the activity of humans or due to, I don't know, deforestation or anything like that. It has nothing to do with anything. Okay? This process of radioactivity itself existed since basically the time when the elements were made from whatever it is, okay? Whether through a Big Bang, for the Big Bang did not make elements, but from stars or whatever process that made them. Okay, some of them are actually made by other radioactive processes. Okay, so it's an unstable atomic nuclei. You have to have an unstable, and then there is an imbalance between neutrons and protons, and this basically leads you to radioactive material. So again, these are the forces inside the nucleus that cause that. So they are occurring everywhere, whether in the sun, the cosmic radiation, or inside the earth. If you go higher and higher in altitude, of course, we'll discover more and more of them because the atmosphere acts as a shield against a lot of them too. And the magnetic field of the Earth deflects a lot of this radiation that is coming from the cosmos toward the North Pole and the South Pole. So that's basically what that is, okay? They are actually high, and there are two types. They are particles and they are EM waves, electromagnetic waves, meaning light, but it's extremely high frequency light, ultra high energy radiation. So this is not the light that you see, okay? This light cannot be seen because it's very, very high. So there are particles and gamma rays, basically. This has a name. When they are extremely high frequency, extremely high energies, they are the gamma rays. And the reason why they are the gamma rays is because nucleus itself is unstable, not the atom. The nucleus itself is unstable and wants to be stable. So when it stabilizes, it does not emit particles. It does not emit electrons or protons or a combination of the two or something. It just emits pure energy. And that energy, because the distances are so small at that scale, the frequencies have to be extremely high and the energies are extremely high. And they can cause a lot of damage, gamma rays. So they are very, very, very damaging. So if there is a bundle of them coming at extreme high rate, they could cause a lot of problem, at least to life minimum, probably even non-life, non-living matter too. So, okay, this is a question. It's kind of silly a little bit. The origins of radioactivity go back to military activities in the 20s. That had nothing to do with it. The Industrial Revolution, no. To the beginning of the human era, the humans said no. Okay, so it has exist before anything. Okay, it has existed on Earth for a long, long time. Fortunately, Earth is big enough that we still have it because we need it. For Mars, for example, it has subsided a lot, at least in the core, to the point that the core actually cooled a lot, and the magnetic field for Mars is basically is gone. Whereas the Earth and Venus, for example, they still have a lot of activity inside their cores. So this has existed since before humans emerged on Earth. So whatever caused humans to start, this has existed there. So it has nothing to do with that. When an atom undergoes radioactive decay, well, honestly, it has to depend on the decay itself. If it's a gamma ray, sometimes it doesn't. There is no change in the element, but in general, it becomes an ion of the same element. Not necessarily becomes an isotope of the same element. Not necessarily. Okay, turns into a completely different element. That is actually what's going on. becomes completely different chemical element altogether. It moves in the periodic table, either toward the left or toward the right, depending on the type of radioactivity. And there are three of them, okay? There is this alpha particle. An alpha particle is nothing but the ion or the nucleus of the helium, nucleus of helium. So when it emerges from material like, for example, radium in this case, it's going to come out without electrons. So it's going to come out positively charged. So if you put it in a magnet between the ends of a magnet, and the magnet, of course, has a north and a south to it, depending on how it's coming. Let's say, for example, it's moving this way. So this is the velocity with which they are moving. And if this is the magnetic field, it's pointing this way. So they're going to deflect along this direction, actually, along the perpendicular direction, or it's going to curl around in this direction because it's positively charged, okay? And negatively charged will deflect also, but in the opposite direction because of its charge is negative. So in this case, the beta radiation, which is actually electrons, they're going to deflect in the opposite direction toward where the alpha particles are. So if you're collecting them, you will see that this is extremely heavy, okay? And they will have a higher deflection because of their mass. Their inertia is very high. This ones, they're less massive. They will be deflecting right away, okay, because they're electrons. And then there is another type of radiation that has no positive charge or no negative charge, and that goes straight through the magnet without being affected by it because they have zero charge. So, and these are the gamma rays, okay? So these have no charge, but extremely high energy particles, okay? And they cannot be stopped by anything. This one can be stopped easily by simple, basically, barriers. This one, to some extent, they can be stopped also, but not as easily as this one because they have less mass, okay? And less charge, actually, too, because this one has two positive charges, so they can interact easily with the environment surrounding them. The minute they gain two charges, and that's it, they're done. They're basically, they become helium at that point. And helium is inert. It's not going to interact with anything. It's going to do not going to do any harm. This electron, though, can basically be absorbed by other atoms and also is gone too. But the gamma rays, they can go through unimpeded. Of course, because they have a short wavelength, they cannot travel very far. But wherever they travel, they cause a lot of damage because of their extreme high energy. Obviously, this too, they have energy too. This one has kinetic energy. And kinetic energy is 1/2 of mass times the velocity squared, and that could do damage too, and they do. The same thing goes for these guys too. So they have also kinetic energy too. So they could transfer heat and they could cause all kinds of problems too. So gamma rays, I mean, radiation in general is not something pleasant to be next to if you are trying to. So the types are the alpha particles, okay? Consists of 2 protons and 2 neutrons. And that's the nucleus, basically, of the nucleus of helium. Loses energy quickly during interactions. Can be stopped by a few pieces of paper, okay, due to its large mass and twice charge. Okay, it's positive charge, but it's twice as much. So it does not penetrate highly lightweight materials. So clothing can be enough to protect you from it. Causes significant damage to the surface of a material. The surface itself, when it touches it, because it has tremendous amount of kinetic energy when it comes out, picks up electrons and becomes harmless and is deflected in the presence of the magnetic field or electric field. Both of them actually can do the same thing, and that is because they are charged particles moving inside these fields. Beta particles, they're basically electrons, okay? Not all beta particles, basically, they're sometimes some radioactive, I mean, I know it's an introduction and we're not supposed to go to a lot of detail, but sometimes actually beta particles can be positively charged too. So it can be either an electron or a positron. So the point being in here is an injected electron from a neutron. Typically you have a neutron, which has 0 charge, going into a proton, which is a positively charged, same mass, similar mass at least, plus an electron, okay? And that electron is the so-called beta particle, okay? So has both a smaller mass and an electric charge. So its mass is small because remember the mass of the proton or that of neutron is about 1800 times that of the electron. Then an alpha particle, but it's a lot smaller than the alpha particle because the alpha particle is 4 times as heavy. So it's 4 times, so it's about 6 times, what is it, 8,000 times heavier than the alpha particle, than the beta particle. Loses energy at slower rate because again, it has tremendous, very small mass, so it's going to lose it, but not at the same rate. Can be stopped by several sheets of aluminum foil now. Penetrates fairly deeply into skin, potential for harming or even killing living cells. Okay. Once stopped, becomes an ordinary electron. So basically, it becomes part of whatever it is. It's deflected also in the presence of a magnetic or electric field because of the fact that it is charged particle. Gamma rays, on the other hand, are extremely high energy radiation, electromagnetic radiation. That means electric field and magnetic field. So extremely high electric field. Okay. High frequency, that is, high energy, are emitted when a nucleus is excited and its state moves to a lower energy state and more harmful than alpha and beta particles. Penetrates, they are mostly penetrating because they have no mass or charge. So they can penetrate almost anything, which makes it very, very hard for us to really use, for example, telescopes used for gamma rays. So it's very, very highly technical thing to do that. Are pure energy greater per photon than an invisible or ultraviolet and X-ray radiation. So they're extremely high energy, greater than, of course, the visible light, which is less than the ultraviolet light, which is less than the X-ray, and the X-rays are actually less than the gamma rays. So the extreme high energy are unaffected by, so they cannot, because they don't have charge. So the electric field or the magnetic field does not affect them. So these are the differences between the three radiations, the three types of radiations. So which of this is the nucleus of the helium atom? The helium atom is the alpha particle. That's its nucleus, okay? Because the alpha particle is made up of 2 protons and 2 neutrons, okay? The 0 in this case symbolizes the fact that it has 0 charge, okay? And it has no electrons. So it's just basically the nucleus by itself. Which makes me to the point that I was talking about earlier, namely the strong forces. They act on a short range. This is the difference between them and the nuclear and the other forces. For example, gravity acts at any distance. Doesn't matter how far you are. The sun and the earth are 150 million kilometers and they're aware of each other in terms of gravitation. So if you have mass, you play that game. There is no problem with that. And everybody has mass, all particles have mass. So everything in the universe is affected by everything else in the universe due to gravity. Albeit it's extremely weak on the scale I showed earlier, but because of this property, it dominates the universe. Extremely weak. But because regardless of how far apart, they play that game. Now, the electrostatic force also has the same property. If you have a charge, and that is the problem with the electrostatic charge, it doesn't matter how far the charges are. They will interact with one another. The problem is when they cancel one another, then that's it. They're done for. So that's why they interact. For example, they keep the atoms together. They interact on a daily basis, for example. But for the sun and the earth, their charges are completely canceling one another on the average, so they don't impact one another. Okay? The earth has a 0 charge on average. The sun, doesn't matter if it has charge or no charge, doesn't matter in this case because one of them has 0 charge, so it's over. And even the case of the sun, it's also neutral altogether. It has on average 0 charge. So 0 mass, because that's part of the charge conservation too. I mean, we think that the entire charge of the universe is 0. That's why on average, the effect of electrostatic forces on the universe cancel. So the only thing that force remains in this case is this gravity. Now what happened on the small scale, on extremely small scale? At that point, you have the nuclear forces that come into game. If the distances are small enough between the charges, and these are positive charges, both of them are protons, then the repulsion is this much. okay? Because they are very close. Remember, the repulsion is inversely proportional to the distance. Now they're very close, so we have a strong repulsion. They don't want to stick to one another. But the nuclear forces are even stronger. And the nuclear forces are always attractive. So they will overpower these guys. And so two protons can stick to one another, not due to this guy, but due to this strong nuclear forces. So that's what fuses the nucleus. That's why you can have two protons next to one another, sticking to one another, despite of the fact that they have positive charges, repelling extremely high repulsion. But that extremely high repulsion is weaker by 100 times, 137 to be more specific, than the strong nuclear forces. You pull them apart a little, okay? This drops practically to zero because these forces, they're completely dependent on how far the nuclei are. The strong nuclear forces are very distance sensitive. They have to be especially at below a certain thing before they start doing their trick. Now, since the protons are far away from each other, these forces drop drastically. Whereas this one's also drop because of the fact that the electrostatic force also is proportional to 1 over distance squared. Obviously, this distance is bigger than this distance, so this has dropped on the scale too, but not by much. Relatively speaking, by this one. In other words, the electrostatic forces are also distance aware because of this relationship, but not as much as the strong nuclear forces, okay? Which, since this one are repulsive now, the two protons fly apart from each other overall. So if you put them close enough from one another, at this point there is a lot of repulsion, so you need a lot of force to keep on bringing them further. It's still dominant, the electrostatic force now compared to the nuclear force, which is very, very insignificant at this point. The minute you get past a certain threshold, at that point the other one takes over and brings them together and fuse the two. So you're trying very hard now to bring them together, still repulsion, and more you close them together, more repulsion, because this distance 1 over distance squared. So now the 1 over distance squared, the distance is smaller, so this force becomes very, very high. You have to overcome it, okay? Once you reach a certain threshold, at that point, the other guy takes over, okay? And will actually bring them together, fuse the two, okay? That is basically the process through which these things work. So we have two forces working against one another. One is always repulsive and one is always attractive. Between similar charges, of course. This one is attractive regardless. Okay, the minute you get two things close from one another, close enough that is, they will take over, okay? So that's why nuclei are stable. The nucleus is stable, okay, because of this force, okay, provided you have that distance small enough. So the strong force is a force in the, it's not in the atom, okay, it's in the nucleus, and holds the nucleons together. So you have two nucleons, proton or a neutron. I mean, this picture, regardless. So if now you have a proton and neutron, and if you put them apart from one another, the force is zero at this point because this guy only cares about charged particles. The electric force only cares about charged particles. So between a neutron, which has zero charge, and a proton, this force is zero regardless of how far you are. Whether you are far away or close enough. But once you are far away, they're basically unaware of each other. They have no idea that they exist from one another. You bring them closer now, they will not resist because there is no electrostatic repulsion now. The minute they pass that threshold, now they're fused actually for the same force. So the strong force now works not just on proton per proton, but it actually works neutron and proton together too. So all nucleons play this game. So this guy is not allowed in this game of electrostatic force, but plays very much the same role in this one. So the neutrons play the role they play in the nuclear forces. So that's why they play a major role in terms of keeping the entire nucleus stable. You need enough of them to keep everything stable. So again, here is another schematic. This is for the alpha particle or the nucleus of the helium. You have attraction because they are close enough now in terms of proton, neutron, and proton, neutron, neutron, proton, neutron, proton, and proton, proton. So you have all these forces. Here is neutron, proton, neutron, proton, neutron, proton, neutron, proton, and in here also between neutron and proton. You have all of these forces keeping everything together, and that is the nuclear forces. And they are stronger than this repulsion, which is very high at this distance, but it's the only one that is happening in there. So this whole thing on average is stable. I mean, this force actually is weaker than there's just this attraction between this proton and proton. And now add to it, there is more attraction in the entire structure. So that's why this thing is stable. So there is repulsion, I grant you that in here, but that repulsion between a proton and proton is weaker than an attraction due to nuclear forces between a proton and proton itself. Add to it more attractions between a proton and a neutron, and between a neutron and a neutron, and it's pairing all of them. Whereas in this case, it pairs only between two of them. So overall, the helium nucleus is stable. It's not going anywhere because of these nuclear forces. But if I take a heavier atom, now, here is the trouble with it. Much heavier atom, for example, between this proton and this proton, there is attraction both ways, okay, due to the help of our friends, the neutrons, and between them because they're close enough. And there is repulsion also. And that repulsion now, albeit there, it's weaker than this attraction. So these two, they're fine. Same thing with these two guys. They're fine. The trouble is, take any of the two that are far away. In terms of nuclear forces, they're very far away for them to be stable. They're meant to be affecting one another. So the only thing that exists between them is actually this electrostatic repulsion. Okay? Now you throw in a bunch of neutrons to try to keep them from flying from one another, and that might do the trick up to a certain point. After that, not enough of that will do it. As a matter of fact, the entire thing becomes unstable. Okay? That's how you explain stability. So smaller nuclei with the small atomic masses, they are stable. The more you start to go higher and higher, this electrostatic forces between one end of the nucleus and the other end of the nucleus start to take over and keep now the whole thing from being really stable. Okay. So that is in terms of the stability using both forces. Okay. Half-life is the rate at which, like I mentioned before, is the time required for half of the substance to go away. It's a constant. It's a property of the material, actually. And this is actually due to the weak nuclear forces that I'm not mentioning in here as much detail as the other two forces. And they acted between them. And they are the ones responsible, actually, for example, a neutron by itself splitting in two, going into a proton and an electron. So there is no electrostatic force in here. There is nothing in here. So bang. As a matter of fact, if you take a proton and you put it next to an electron, technically they should attract one another to form a neutron. But that neutron itself is actually unstable. It splits in apart. And there is no nuclear force to explain that, at least in strong nuclear forces. So there is the weak nuclear forces responsible for these forces. That's the fourth kind of force that we're not going into a lot of details in it. So the half-life is the time it takes for half the substance to basically change to a different substance. So a certain isotope has a half-life of 1 day. This means that the amount of isotope remaining, so in 1 day, day one, at the end of day one, I would half the substance now is still here, and the other half has changed to something else. So this is else. This is the substance itself. Now, after another half day, after another day, another half of the substance. So remember, this was half the else now that we got from it from the first day. Now, this one also will split to another half too. So this is what is left now of the substance. So half the half. So this is the half of the first day. Now, this is the half of the half, which is a quarter. Okay, so 1/4 should be the correct answer. If I wait 3 days, it's half the half of the half, which is 1/8. If I wait 4 days, again, it's going to be 1/16, and so on and so forth. And this is a graphic showing that, okay? So we start with 1 kilogram. After, for example, we're taking, which element is this one? Is it carbon? No, it's not carbon. Carbon is 5,000 something. Anyway, it's a substance that has 1,620 days, okay? So 1,620 years, I'm sorry. So if I wait 1,620 years, I have half the blue left. If I wait twice as much as 1/4 of the blue. If I wait 4,860 days, years, I'm sorry, I'm going to end up with half the half of the half, which is 1/8, okay? And so on and so forth. So actually, if you are trying to follow to see when I'm going to end up really with 0, technically there is no limit. This extends forever. It's never going to reach 0. It's always going to be half of whatever you started with. So transmutation is a change of an element from one kind to another. For example, in this nuclear reaction, what we have a capture of a neutron. And a neutron in this case will change the atomic number in here by the atomic mass in here from 14 to 15, okay? And then this one changes the number in here. So you have 7 plus 1, that's 8. But one of the protons actually is ejected in this nuclear reactions, which is the ion for the hydrogen atom. And basically now you have the complete different atomic number. You have a complete different element. You start with nitrogen, and you end up with carbon. Okay, complete different one. And you have moved actually in the periodic table from this group to this group. Okay, from one side to another side. You moved from chemistry to another chemistry. And it can happen naturally, and also it can happen artificially. We can do that if it requires energy. Now, for example, in the case of uranium, you have uranium 92, that's its atomic number, to thorium, which is a different element. Why is it not drawing? Okay, so you start with 92. You end up with 90, so you moved back twice, okay? From 92 to 91 to 90, and you emitted now an alpha particle. This number in here may be misleading. You may think that you have 20, but it's not 20, 20 zeros. 2 zeros, 2 neutrally charged particles, which means that they are protons, okay? That's the symbol I've been using. For neutrons, that's the symbol I was using all along for neutrons. So you have 2 protons and 2 neutrons, and that is basically for an atomic mass of 4. Because you add up the 2 numbers, and that is the helium nucleus. So now the point in here is that you started with one side, and you moved 2 groups basically from this group down twice, okay, to another group in terms of the periodic table, to thorium. Okay, so this is a completely different element than what you started with. For the beta emission, there is no change in the mass in this case. The atomic number changes by 1 because of the fact that you changed probably a neutron to a proton. So now you actually move to the other side. Okay, you increase the atomic mass in this case, the atomic number in this case, but the mass number stays the same because you did not gain nucleons or lose nucleons. Because one nucleon, which is a neutron, has changed to a proton, so which is another nucleon. So in terms of mass number, it did not change at all. In terms of chemistry, also changed. It's no longer in the same group. Now it has moved to a completely different group, okay? Gamma rays don't change the mass number and do not change the atomic number, because you're not gaining nucleons or losing nucleons in the process, so you still have the same number of nucleons that you start with. And actually, the atomic mass also doesn't, the atomic number also doesn't change, in the sense that you stay in the same group. On the periodic table, you are actually in the same element, okay? So that's, again, this is another nuclear reaction in here. So you have an alpha particle with 2 protons and 2 neutrons heading nitrogen in here. And what happened in this case, you end up with an oxygen plus the hydrogen nucleus, okay? So that's the nuclear reaction. Whether this nuclear reaction can happen naturally or not depends, of course, on the energy. If the operation happens free, if it can happen while this one is not moving, then it doesn't require energy, and the whole operation will give you actually energy, or at least end up happening without any energy. Or you will need probably some energy, and probably that's what this representation in here with this velocity, which is the kinetic energy. So it has to have a lot of energy for it to be absorbed by the other nucleus, okay? So when an element ejects an alpha particle, the atomic number of the resulting element reduces by 2. Like the case of, for example, uranium-92 going to thorium. So in this case, it reduces by 2. So once you elect, an alpha particle will take 2 protons. So whatever you started with, you lost 2 protons from where you were. So the atomic number must have dropped by 2. When an element ejects a beta particle, the atomic number of that element actually is increased by 1. Okay? Because again, whatever that number of protons now, and now you have, so if you have, let's say, for example, 10 positive charges in there, now negative charge emitted, so whatever happened in there, you're going to end up with to keep the charge the same. So if you have 10 positive charges to begin with inside the nucleus, and now negative 1 of them has left. That's what the beta particle is. So in order to keep 10 positive charges equal to 10 positive charges, you must have ended up with 11 positive charges. 11 minus 1 is still 10. So you must have moved up. You must have increased the atomic number in this case by 1. Okay. Well, it's for the alpha, for the okay, a certain element emits 1 alpha particle, and its product then emits 2 beta particles in succession. So this is the problem. So an alpha particle will move it twice to this side. If you want to, it goes -2 twice. One beta particle will move it once plus, another beta particle will move it once plus. So at the end, you end up with nothing. You end up with no change at all. Okay? So the atomic number would have stayed the same. I mean, it would have moved twice in here and moved twice back this way. So it ends up back to where it started from. It moves twice this way and moves twice back to where it started from. So it's the same element. In other words, you might have a different isotope, and it is, but that's the same element. I mean, chemically, that's the same element in terms of chemistry. It's in the same group, really. Moved down 2 groups this way, and then moved 1 group back and another group back to where it was in before. It may have a different atomic mass, which is in this case an isotope of the original element. Okay, carbon dating used for plants and animals based upon the ratio of how much carbon-12 and 14 are. The half-life of carbon-14 is 5,760 years. The method depends sometimes on the production of carbon-14 in plants. So here is the deal. Plants on their own, they produce carbon-14. Okay, that's part of their life cycle. Okay, take any plant, depending on the plant, it gives you this much carbon-14. The plant dies. At that point, there is no more production of carbon-14. Carbon-14 by itself will decay half of it to carbon-12. That's similar to the process we were talking about. It stays in the same group. So it's still carbon, but its atomic mass at the end has changed by 2, okay? That's it. Now, you come after that plant dies, a long time after it dies, and you measure how much carbon-14 now I have, Okay, you know the plant, you know how much you're supposed to have, you know how much the ratio of carbon-14 to carbon-12 is. That's what you're trying to find. And if you find, for example, on half of carbon-14, I mean, the carbon-14 and carbon-12 are exactly the same mass when you do a spectral analysis or whatever you want to determine this. Once you find them, you say, oh, wait a minute. This plant must have died about 5,760 years ago. If you find that it's actually the ratio tilted toward more carbon-14 than carbon-12, then you must have been a lot younger than that. If you find actually it's less, then it's actually has done a lot earlier than this. So based on that ratio, you can determine the age of that plant. When was it the last time it was basically living? When was it the last time it was producing carbon-14? So that's how you use carbon dating. That's how you use radiometric dating, radioactivity actually to date things for you. And it's not just good for carbon, it's good for any element that you know its life, okay? Obviously, we cannot use carbon, for example, for dating the life of the entire planet, for example, which we know it's about 4.5 billion years ago. So if I do that, then probably we'll have no carbon-14. First of all, there were no plants then at that time. And plants only appeared less than a billion years ago, okay? So that's useless. So we have to have a different mechanism, besides of the fact that we cannot even find those. And that's why we use other elements to do that. And it improves the precision, number one, and it also because of the availability of those elements. So we use other elements for dating the planet in geology. An archaeological dig uncovers an ancient spear whose wooden handle contains an eighth of the radiocarbon of a fresh piece of wood. About how old is the spear? Okay, that's easy. I do the ratio, and it's an eighth. I know 5,760 years ago, it was half. It would have been half. Well, twice as much, 11,000 something. It's going to be this much, about a quarter left. But I don't have a quarter. I have actually an eighth left. Okay. So it's actually another 5,700 in addition to the 11,000. So it puts it at 17,280 years, plus or minus, of course, for fluctuations and the errors. 17,000 years to be more specific. Okay. So that's probably when the Neanderthals and the humans were met in southern Spain. That is the date, roughly. It's actually a little longer, earlier than that, but that's the date when these things were. So this is based on almost accurate studies that were done in southern Spain, modern Spain, and southern France, when humans, hominids, basically, the humans, actually, the modern human, crossed towards Europe and from Africa and met with the Neanderthals. I think it's a little earlier than that. But that's, anyway, ignore the example I was talking about, but that's basically this example, and it gives you an idea of how archaeologists actually do stuff in there. So when they're talking about with knowledge. They are not talking with theory only. Okay, fission is a process basically of taking atoms and splitting them. Basically, what it is you take a heavy atom, in this case uranium-235, which is radioactive. I mean, which can do this reaction a lot easier than 238. 238 is not is more stable than this one. So this one is a little bit unstable. The minute you throw in a neutron at it, which is negative, has zero charge in it, it's going to shake it a little, and that shaking will make the charges move further away, and then the whole thing starts to split because of the electrostatic force that we were talking about now. The charges have moved far away from each other to the point here that now the nuclear forces will not sustain this one. When it does, it's going to release energy. So this is an exothermic nuclear reaction, so it's going to produce energy for us. It's going to release the energy that was bonding these two things together. And as a byproduct, it's going to give us actually 3 neutrons. And the 3 neutrons can be used to trigger more nuclear reactions. So we can take this one and hit another atom. We can take this one and hit another atom. And we take this one and hit another atom of the same type. And now that nuclear reaction can trigger 3 more. And this 3 more can trigger each one of them 3. So I'll have 3 times 3, which is 9. And then I will have 9 times 9, which is 81. And then 81 times, and you can imagine the process basically proliferating in an indefinite fashion just by one. The whole thing can trigger. Obviously, I need a certain minimum mass for this whole thing to happen, for this nuclear reaction to happen. If I want to make a bomb, this is what the bomb is. If I am a nuclear reactor, I have to control that. I don't want all 3 of them to go and hit other uranium-235. I want just this much, okay? So there are rods actually in a nuclear reactor that you can lower them to basically absorb some of this neutrons, and at the end you have controlled actually the nuclear reaction, and that's what the nuclear reactor is actually. It's controlled reaction versus a nuclear bomb where you have minimum amount of mass, where this reaction goes under basically without control, and the whole thing starts and never ends to the point it consumes the whole thing. So you start with a certain amount of mass of uranium-235, it's all consumed, and that is what the nuclear bomb is. So that's the difference between them. The difference between them, the 2 reactions, is controlling these guys that emerge from this reaction. One of them is controlled in purpose with a minimum mass that is needed. Once you have that, you have a nuclear bomb. Another one, you want to control these guys. You want to have them, you want to even kill the whole thing. You want to turn off the whole nuclear reactor. So you want to stop all of them, okay? So if there is a power shutdown, that's what you do, okay, in a nuclear reactor. And if you want to increase the power, to deliver more power, you're going to have it, but you have to be very careful not to have the whole nuclear reactor explode. So that's, again, the principle behind it for the nuclear fission. This is basically what I was talking about. Whatever emerges, some of them, of course, they go and interact without any interactions, but if you want them to all interact, you have to have enough material in there, dense enough for you to happen. So this one will trigger another reaction, this one trigger another reaction, this one trigger another reaction, and so on and so forth. And the whole process continue without stop until everything is gone. So the critical mass is what I was talking about, is the minimum mass of fissionable material in a reactor or nuclear bomb that will sustain a chain reaction, okay? Obviously, even in a reactor, you need that too. Otherwise, it's going to die immediately after the first few. So you need that, but the only difference between a reactor and a bomb is one of them you want to control it all the time. Okay? A mass large enough to sustain fission, at or above critical mass in a large quantity of atoms, an enormous explosion can occur. Okay. 235 of uranium-235, uranium-238, and uranium-239 are all isotopes, okay, of the same thing, which is uranium. In nature, this one dominates all of them in terms of how much it is, okay? Which brings us to another point in here, trying to understand how energy is released in a nuclear reaction. And this is the famous E equals to mc squared that Mr. Einstein has discovered in the early 1900s. And if you think about it, this relationship tells you that energy is mass. Because that C squared is just a number. C squared is just 300 million squared, that's all, 300 million meter per second squared. So it's 300 million meter per second squared, that is. It's a huge number. So you don't need that much mass, because whatever tiny amount of M converts to energy, you'll have a tremendous amount of energy. That is the energy released during fission or fusion, okay? So during a fission or fusion, during a nuclear reaction, what you're interested in is how much change in mass there is. Because a proton by itself has a lot of mass. When you have two protons together, in order for that nuclear reaction to happen, actually some of their mass is actually ejected. And that is to help them fuse. So that energy, that if you weigh the mass of a proton, while it's bounded, it's less than the mass of the proton before it's bonding, because they have to give some of that energy together to help them fuse to one another. So that's basically how the interaction. And this is true for all actually forms of energy. This relationship is true everywhere. not just for the nucleus. So if I want to draw nuclear to mass to atomic number, the nuclear mass to atomic number, this is basically the relationship with which they go. And obviously, which nuclei has the greater mass, the more the one that has the higher number of nucleons. In this case, uranium, more than hydrogen. Hydrogen has only one nucleon, okay? Iron and lead have less than uranium. This is what I was talking about in terms of the star before. If I plot the mass per nucleon, how much mass per nucleon? Because every nucleon, when they come together, they give some of their mass for this bonding to happen, okay? So what I do in this case, I take the entire mass of the nucleus and divide it by how many they are. In the case of uranium, I have, what is it, 235, I have 235 of them. Uranium-238, I have 238. So take the mass of all the nucleons, not just of the protons, and divide them by their number. Obviously, for the hydrogen, I only have one proton. So this is basically the starting point. It's extremely high ratio. And then for uranium, it's in here. Iron is the least number of mass per nucleon there is. So it's the most stable element in the periodic table when it comes to nuclear forces. That's why stars start to fuse early on in their life, only hydrogen, making helium. And then later on, when they run out of hydrogen in their core, they start actually fusing heavier helium and more elements, making stuff. That's fine. The sun probably will reach some stage in here in carbon and stop, and then basically becomes a white dwarf. Other stars that are bigger and bigger, they can continue making heavier and heavier elements when they run out of the hydrogen in their core, of course. The minute they make iron, because it's the most stable, that's it. They collapse on themselves. And when they collapse, they actually explode in a huge fashion that can make more elements in the process, okay? That is because of that huge explosion that others. So star doesn't make the others. It's supernova that makes the heavier elements, okay? That's the process through which. So that's why iron sits right. It has this special property, okay? Think about it when you grab your spoon today for your lunch. That is the cause of death for the stars. So if there is anything that can overpower star, that is that spoon, okay? In which of this nuclei does the proton have the greatest mass? Of course, it's the hydrogen. You saw it from the curve. Because it is not bounded to anything. It doesn't give any energy to anybody. It's just by itself. In which of this nuclei does the proton have the least? Oh, just mentioned it. It's this guy. Okay. Here is the curve again. This is the least. Okay. These are higher. These are higher. Anybody else other than iron is higher than it. On this side, you have fission. When they split, they give more energy. On this side, though, we have the next topic, which is the fusion. We still have a few minutes. Okay. We have the nuclear fusion. Again, when they fuse, they give that energy basically for them. So they give some of the energy in order for them, some of their mass in the form of energy in order for them to fuse. Here is the graphics for it, okay? So in here, this is isotopes of hydrogen. You have deuterium in this case, it's called, which is a hydrogen made up of both proton and neutron inside their nucleus. And now when they fuse, they give actually more energy because they make hydrogen, make helium in this case, okay? And of course, it's less and less mass because of that energy that they exchange in the process. Nuclear fusion is produced by high temperature resulting in, okay, the thing with the fusion is the confinement. The biggest problem with fusion is how to confine, because they are positively charged and nuclear forces, electrostatic forces prevent them from getting closer enough to one another. Once they get close enough, of course, they will fuse because of this process and they will give you energy. So that's really, and usually they have to have a lot of heat to keep them together. And this is, in a sense, how nuclear bombs also happen in terms of the hydrogen bomb, not the A bomb. The first one I was talking about in the case of fusion, that's the atomic bomb. This one actually is the hydrogen bomb, and the hydrogen bomb actually is, in a sense, you have nuclei sitting around an A bomb, an atomic bomb, and that is the one that provides the heat enough for them and triggers the second bomb, which is really a more deadlier one, more energy than the first one. Actually, you can see it from this curve, okay? This line in here is much, much higher than this line. So there is more energy released in this process than in this one, at least the curvature is. So because in here you will get only this much energy versus this much energy for the same nuclear reactions. So this has the potential of providing a lot more energy. That's actually what powers the stars, because it has a tremendous amount of energy that can stay for billions of years, possibly for the smaller stars much longer than that, without having to run out of energy. Because of this, they only need to change a small amount to sustain themselves, whereas this one in here requires far more energy. This is not to compare it with the burning fuel, for example. That is even worse than this. So burning fuel would transfer even a tinier amount of mass. So that is completely nonsense. So stars are not wood burning, because if it was, the star would not last long enough for it to be seen today. It would not last billions of years as we know it. Again, this is basically in a nutshell that discussion I was talking about. And we have a couple of questions. When energy is released by the process of fission or fusion, the total mass of the material after the event is, of course, less, because that energy is released. Where is it coming from? The energy is the change in mass in this case, times the speed squared, the speed of light squared. That is the energy released. So it's gone. So their mass has reduced by this amount. And the amount is energy released divided by the speed of light squared. So this is in a nutshell the chapter. I know it's not part of this exam, but it's part of the next exam, exam 3. So I hope you guys took, first of all, the question of the day. Remember, it was the 4 forces in nature. And the other thing also is the review for the exam, which I hope that everybody will take care of. And then the second point is the exam. And after that, we will have a quiz for this chapter. These 2 chapters, this week chapters. Okay. If you guys don't have any questions, I will see you guys. I probably will not meet on Tuesday, okay? There is no class on Tuesday. I will make an announcement of it so that you guys don't wait for me at 8:30 in the morning on Tuesday, because I suppose some of you are still taking the exam then. So we will not have a live session on Tuesday next week. But because I will also be monitoring some of the questions that you guys will have, we will in discussion designated for this exam. And we will meet a week from today, 8:30, the same time, discussing the next chapter and basically elements of chemistry. Good?
All good.
Okay, see you guys. Let me stop the recording first.
Mm-hmm.